This demo shows how to transfer Grasshopper models that use volumes directly into LUSAs. In this example, we're looking at a reinforced concrete deep beam. The setup is pretty straightforward. The parameters here define the beam's dimensions, and then the distance from the concrete face to the center line of the rebar, and the mesh size. The next block here generates all the lines required to create the volume. Next, we can see the LUSAs plugin in action. The volume member component takes the parametrically defined volume from Grasshopper as a parameter and creates the corresponding LUSAs volume member. The volume mesh component specifies the element type and assigns it to that new member. These can be found up here. To make the simulation more realistic, a nonlinear concrete material attribute is defined and applied to the volume. This is achieved via the custom attribute component, where the corresponding LPI script can be copied directly from LUSAs and pasted here. The reinforcement is modeled using parasitic bar elements, again via the custom attribute component. These are particularly efficient because they don't require the rebar and concrete meshes to match. The software automatically handles the interaction by transferring stresses and strains between the rebar and the surrounding concrete, assuming perfect bond conditions. Additional components in the script define and assign boundary conditions under the beam supports and apply a patch load on the top surface of the beam. If I were to double-click this button, the LUSAs model would automatically regenerate and update. Since the analysis has already been run, let's move straight to the results. Here, in the attributes tree view, we can confirm that all materials, mesh attributes, and loads were correctly created. One step that was done manually was the definition of nonlinear load case controls to be able to run a nonlinear analysis. Let's now examine the load versus displacement curve at midspan. We can see that plasticity begins to develop at a total load factor of about 1.3. Checking the crack pattern. This value indeed corresponds to the onset of cracking, 1.3. Cracking then propagates through the beam's depth until the model reaches instability. Finally, let's look at the tensile force in the rebar at midspan. As expected, once cracking occurs in the concrete, a significant portion of the tensile load is transferred to the reinforcement. This concludes our simple example demonstrating how to define and export solid parametrically defined models in Grasshopper directly to LUSAs, a capability fully supported from version 23 onwards.